Hi, it's Andrea Stocco here from the Software Institute at USI, Switzerland. In this video, I will shortly present you our research on predicting misbehaviors in DNN-based self-driving cars. In a very simplified scenario, testing a DNN that performs the task of driving is done as follows. First, human drivers drive camera-equipped cars and record driving data. Particularly, each front image seen by the car is associated to the steering angle and brake commands by the human driver. All these data are then used to train a neural network that imitates the behavior of the driver. Once the model is trained, it is further tested on simulation platforms until a certain adequacy criteria is met. Then, the model is deployed on a real car and it is further tested in the field. So, what is a misbehavior for this kind of software? A misbehavior is nothing more than a deviation from the test requirements, and the main test requirement here is that the car should stay on road. Suppose that this input image is given to the car, and that the DNN outputs this steering angle. Regardless the fact that the input is known or unseen, the DNN will always make a prediction. In practice, thus, we cannot access the reliability of a DNN-based autonomous driving system if we study the model in isolation, because we need to observe whether the causal effects of wrong predictions on the driving quality. And this can be done only in field or more conveniently through a simulation platform. In the context of our research, we use the Udacity simulator for self-driving cars, which allows to connect a deep neural network that imitates the driving behavior. The main limitation of this approach, however, is that it is virtually impossible to account for all driving conditions at training time. Therefore, there will always be that one situation that is unknown that might cause the car to misbehave. The objective of this research is therefore to try predict whether a car is facing an unsupported scenario before the actual misbehaviors are observed. Our main approach revolves around monitoring the uncertainty of the driving scenario as the car drives and set a threshold that determines whether the uncertainty is rising over an acceptable level. In practice, our approach consists in a redundant component that analyzes the data fed to the car and warns the system if appropriate. As the core component of our technique, we use autoencoders that are neural networks that are capable of reconstructing the inputs they are given with high fidelity. The rationale of using autoencoders for anomaly detection is that the misbehavior predictor will be able to reconstruct well inputs similar to the ones it was trained with, whereas it will fail to reconstruct inputs that are unknown, hence potentially unsupported by the car. We studied different autoencoder architectures and compared it with the input validation strategy of deep road. Our experimental setting consists of different tracks and weather conditions. Particularly, we used the sunny condition as nominal and studied the effectiveness of our misbehavior predictor in recognizing when the car is facing an unseen condition, such as snow, that ultimately lead our model to crash or go out of track several hundred times. In brief, our results show that our autoencoder-based approach is more effective at predicting misbehaviors with a factor of 3 over an existing technique, when the ratio of accepted false positive is set to 5%. To conclude this overview, I presented a technique to perform online misbehavior prediction for autonomous driving system, which is promising. If you want to know more, you can download our tool and our simulation platform, as well as follow the presentation at the main track on July 7th. Thank you for your attention.